All right, so let's talk about the question I asked in the discussion question for Module 8. So the point of this question was to illustrate why the two conditions of the mean value theorem are both necessary. So what I want to do here is basically, once for continuity, once for differentiability, basically eliminate one of those conditions and show that the mean value theorem might not hold at all. So what happens if f is not continuous on some closed interval? So let's do this. I think I can show this graphically. So let's have our closed interval be a unit interval, so from 0 to 1. So let's say I have a function that passes through the origin and also passes through the point. I'm kind of exaggerating my scales here, the point 1, 1. But I have a function that I don't need to be continuous. I'm ignoring the continuity condition. So let's say my function looks like this. It has two horizontal line segments, one that follows the x-axis, and then it goes to a jump discontinuity like this. So let's say right in the middle of this interval, so at 0.5, I have this jump discontinuity. So now what I want to show here is that the mean value theorem, the conclusion of it, namely that so let's remind ourselves what the conclusion of the mean value theorem is. Basically, if you have a function that's continuous on a closed interval and differentiable on the same open interval, what's guaranteed is that you have this. You have a C that's in between A and B, such that f prime of C is equal to f of B minus f of A over B minus A. Or it seems like a lot of the language that you all prefer is this. Basically, the instantaneous rate of change at a single point in the interval matches the average rate of change taken across the entire interval. So let's do this. Let's now find the average rate of change. So the average rate of change is what? It's f of 1 minus f of 0 over 1 minus 0. F of 1 in this case is 1. F of 0 is 0. So basically my average rate of change is 1. So if I were to connect these 2 points with a secant line, this slope would be 1. So is there a point on this interval where the derivative of the function is equal to 1? And the answer is no, because I have two horizontal line segments. So wherever the derivative is defined, the derivative is equal to 0. So the mean value theorem does not apply here. Or the conclusion of the mean value theorem is not satisfied. So on the other hand, what if we say we have continuity over the interval, but we don't have differentiability? So let's stick with the same interval 0, 1. And let's do this function. Let's do this like a triangle function. So from 0 to 1. And I want to have a function that looks like this. So at x equals 0.5, I have y equals 1. So let's say I have a straight line connecting 0, 0, and 0.51, and then another straight line connecting the point 0.51 to 1, 0. So I have continuity, but why don't I have differentiability? Well, at this single point here, where there's a hard corner, I do not have differentiability. So I have a function that's differentiable on almost every point except for x equals 0.5. So what does that mean about the conclusion of the mean value theorem? So let's find the average rate of change. That's equal to f of 1 minus f of 0 over 1 minus 0. F of 1 and f of 0 are both 0. So what's my slope? 0. So is there anywhere on this function that has a slope, like an instantaneous rate of change of 0? So I only have two slopes here, one on either side of this cusp. What's the slope here? So if I go upwards by 1 unit and to the right by half a unit, that slope is going to be 2. So on this upward trajectory, my slope is 2. And by symmetry, on this downward slope or downward trajectory, my slope is -2. So at no point is the derivative of this function equal to 0. So all that to say that in order for the conclusion of the mean value theorem to be guaranteed, you have to have both these conditions.